Dear audience, dear professors, it's my pleasure and honor to come to India for the first time and to talk at this remarkable school, to this remarkable audience. I'm grateful to the organizers, and I'm grateful to Vishal Sahni for his relentless efforts to make my visit possible. I'm not going to deliver any deep philosophy today. Rather, I would talk about my more or less personal impressions, even emotions, how quantum information has been influencing, has been transforming my views on physics, on science, especially on foundations of physics, and on quantum mechanics itself. When quantum mechanics was very young, it was only considered as a theory for black-body radiation first, then atoms and molecules, as the theory of the microscopic world. But gradually, scientists, physicists realized that quantum mechanics could be extended for more and more fields, more and more phenomena. For the electron, for condensed matter, for electrodynamics, for nuclei. The time scale is about the mid of the previous century here. Then quantum mechanics extended itself for elementary particles, and then in the rest of the past century, people sought to extend quantum mechanics for gravitation, cosmology, information, biologic, material, brain and consciousness. You may notice the question marks here, because all these concepts, theories, as quantum theories, are not fully and ultimately confirmed. The only exception is information, where we have safe statements and firm quantum theory. So the subject of the school is an exception. It's peculiar because it belongs to the series of steps where quantum mechanics was being extended for radically new phenomena, but without the question mark and with confirmed knowledge. When I was young, we had a different approach to quantum theory than we have today. Quantumness meant just the discreteness of the theory, that it was able to describe discrete values, discrete energy values, energy gaps, etc., instead of the continuous notion of physical values in classical physics. The state vector psi was almost the only, was almost extensively used to describe a quantum state. And the density matrix was rarely invoked. When I was young, it was only taught for the spin states and for the Gibbs statistical ensembles. The Shannon information theory, however, it was a lovely and famous theory, and all physics students had been aware of its existence, but it was not taught in standard physicist curriculum because it had limited interest in physics. And another thing which was then different from our contemporary situation is that in principle quantum mechanics was taught as a theory valid for single quantum systems, but it was not testable at all on single systems. It was just testable on ensembles. And today, quantumness means something different, at least in modern courses of quantum mechanics. It means entanglement. It means that quantumness may enhance the capacity of information treatment, meaning computation or encoding or metrology. And the density matrix, rho with the hat in my notations, is now recognized and taught as the generic and most general mathematical object to represent a quantum state, which is in general not a pure state corresponding to a state vector, but in general a quantum state must be a mixed state, only tractable by the density matrix. And another comparison with the Shannon option. Quantum information is exciting, is continuously and permanently exciting physics. So Shannon is now taught and credited to a much higher level than before. And also single quantum systems are now available and testable. And this makes a huge difference, in our experimental capacities compared to half a century before. Now, I'm going to illustrate my experiences, how my quantum information studies and investigations has changed my views on the foundations of quantum mechanics. Quite a time ago, Wouters and Zurek proved the famous no-cloning theorem, meaning that you cannot clone a single unknown qubit, for instance. Mathematically, cloning would look like this. You have a single qubit described by single qubit density matrix, and you would produce two independent copies out of a single qubit, which copies could be described by the direct product of the same initial density matrix. Now, according to Wouters and Zurek, this is an impossible process, and this no-go theorem was believed to guarantee the security, the peculiar quantum security of some very important protocols. It is an instance when you learn something negative, something sort of no-go, and you exploit it. You turn it into something positive. The impossibility of cloning guarantees something affirmative, which is the security of quantum of some quantum protocols. If you cannot copy, you cannot steal a qubit. This is the reason why the Wooten-Zurek no-cloning theorem plays a role in quantum secure protocols. Now, a few years later, Nicolas Gisin proved another famous theorem, that any nonlinear modification of quantum mechanics would lead to some nonsense, which means that if you modify your Schrödinger equation by adding some nonlinear term to it, whatever this Schrödinger equation is, maybe in the simplest case it is the Schrödinger equation of a qubit, whatever nonlinearity you add to it, small, sophisticated, or a heavy nonlinear term you add to the linear, standard linear Schrödinger equation, you become able to send signals faster than light. Usually we don't accept this option, which means that Gisin theorem is an indirect proof against any nonlinear modifications of quantum theory. Now, for quite a while, these two exciting quantum paradoxes invented by Wooten-Zurek and Gisin were believed to be quantum paradoxes. But after some years, 10 or 20 years, we realized that the same paradoxes are valid classically as well. They are not genuine quantum paradoxes. And the details are the following. Look at the classical case. You have a qubit X, and it has some random state, maybe a total random state with equal probabilities 0 and 1, maybe a partial random state. At least initially your qubit has some probability distribution. Now it is an everyday wisdom in classical statistics that if you throw your initial qubit into a classical black box machine and you wait until the transformed qubit reappears at the other end of the black box, the probability distribution rho prime of the new qubit must be a linear map of the initial distribution of the initial qubit. This is an everyday classical wisdom. And nobody would challenge this linearity, because everybody knows that if you violate this linearity, it goes against the statistical interpretation of the probability distribution. You have no statistics then. Look at the cloning issue. If you want to clone your initial bit, I hope I always talk about bit, not qubit. So it's a bit and bit. So if you want to clone the bit, mathematically it would look like this. Rho of X becomes transformed into the product of rho of X. Now, this is forbidden because this is not a linear transformation. This is a quadratic transformation. So, classical cloning is forbidden because it goes against the statistical interpretation of the probability distribution of the bit. Now, if anybody would ever challenge the linearity of the classical black box machine, he or she would easily prove that faster than light communication becomes possible, which is a nonsense. But nobody have ever challenged the linearity of the classical black box machine. Now, we have no such everyday wisdom for qubits, for quantum mechanics. Therefore, from time to time, people, including myself, would propose or consider nonlinear modification of the quantum black box machine. But now we know that for the same reasons as in classical statistics, the nonlinearity of the quantum black box machine would contradict the statistical interpretation of the density matrix. Therefore, after 10, 20 years, meaning after the discovery of the non-cloning theorem and the faster than light anomaly of quantum nonlinearities, now we see that the linearity of the quantum operations, which looks mathematically so, is rooted much deeper than we had thought before. And this was a very crucial experience along my investigations. And another instance is the so-called Perez-Horodetzky entanglement criterion. Now, we know that entanglement had been proposed and recognized by Schrödinger himself, and he, Schrödinger, knew already that the essence of quantumness is in entanglement, not necessarily in the discrete energy spectrum of his equation when applied to a bounded system. So he knew already that entanglement must be number one peculiarity of of the quantum world. Now, for wave functions, for pure states, entanglement just means that if we have two quantum systems, say two qubits, if their quantum state is pure and independent, then you can compose the composite quantum state as the direct product of the two state vectors, meaning the product of the wave functions. If the quantum state of the two qubits is not a product, then they are correlated, they are quantum correlated, and they are entangled. Now, the issue was open for and remained open for a long time for mixed states. For mixed states, in 1989, Werner defined the notion of separability. A mixed state is separable. It means it is not entangled. Separability is the contrary notion to entanglement. So a mixed state is separable if and only if it is a convex mixture, it is a weighted mixture of of product states. Look, if we have two qubits, one belongs to Alice, the other one belongs to Bob, and the set of rho A lambda stands for a set of qubits belonging to Alice. And similarly, the set of rho B lambda, where lambda is a running index, the rho B lambda is a possible set for the density matrices owned, for the qubit owned by Bob. Then a single direct product, rho A times rho A, say lambda, times rho B, the same lambda. A single product corresponds to the composition of the two qubits in an uncorrelated way. So the two qubits remain uncorrelated. But if you introduce the weighted sum of those uncorrelated product states, you get the resulting state correlated. Now, if you can choose the weights positive and summing to the unity, then the resulting state is still separable. It is classically correlated. It is not entangled. So according to Werner, a mixed state remains unentangled, remains separable, if you can write it down into this form. And it is very hard to test. If I give you a state, a composite state of two qubits, it's very hard to prove whether there exists such an expansion of the state or there is no such expansion. If there is no such expansion, then you can claim that the state is entangled. But it is a very hard task, and we had no easy to apply analytic separability test until Perez observation in 1995, who observed that if you apply a partial transpose to a given composite state, and if this state is separable according to Werner, then you get another composite state. So look at this line. Partial transpose means that you only transpose the second part, the Bob part of the composite state. You transpose Bob qubit. Transpose means that you literally transpose the density matrix rho B. Now, look at the separable state. If we apply this partial transpose to a separable state, it remains a separable state. Now, Asher Perez observed that if the state is entangled, meaning that there is no such expansion on the right-hand side, then the partial transpose may destroy the positivity of the state. So the right-hand side may acquire negative eigenvalues as a matrix. So soon after Perez's observation, Horrid proved that in case of two qubits, if we apply this partial transpose, and the result is a legal density matrix with non-negative eigenvalues, then the state is then the initial state rho EB was separable. In the other case, if the state was not separable, then according to the Perez-Horrid test, the partial transpose of the state becomes an indefinite 4 by 4 density matrix. So the partial transpose has been, it was the first and only easy to apply test to reveal the entanglement of a 2-qubit state. And I show you that physicist approach to this very famous and widely applied criterion. I mean, how physicists approach is different, a little bit different. Let's go along the considerations of a physicist. Separability of a composite state is a physical feature, while transpose is a mathematical option. It depends on the representation and the coordinate in which you consider your density matrix. So we need the physical meaning for the transpose, because it is the essential part of the Perez-Horowitz entanglement test. Now, we know from Wigner that the time reversal operator is an anti-unitary operator. And look, the transpose is equivalent with time reversal operation. It is unitary equivalent with time reversal operation. So for a theoretical physicist, the Perez-Horowitz criterion is slightly different and maybe more elaborated physically for a theoretical physicist. Simply, we prefer to apply or to invoke time reversal operation instead of transform. So the Perez-Horowitz criterion for theoretical physicists states that the 2-qubit state rho AB is separable if its partial time reversal is non-negative. So far, we have transformed the mathematical criterion into a physical one. And now, for me, there is at least one exciting consequence of this reformulation of the Perez-Horowitz criterion. And this is that since we know that the partial time reversal of an entangled 2-qubit state is not a state, it means that we should state that the reversal of the local time error is impossible. It may be a quantum cosmological statement that look at the qubit in region A of the universe and look at the qubit in a remote, even decoupled region, and try to invert the local time error of the qubit in region B. Classically, the reversal of the local time error is possible. We have nothing against it. The classical physics remains consistent if you invert the local time in some remote part of the universe. But this thing becomes impossible. It is forbidden because of the existence of entanglement in a quantum world. So the local time reversal is impossible. It's forbidden by quantum mechanics, and I learned it from the Perez-Horowitz criterion after I have reinterpreted the transpose in terms of physical operation, time reversal. It was not new at all, but still, if I guess how many places the Perez-Ferodetsky criterion is being taught for physicists, engineers, or communication experts, I think that it is quite rare that this physical background is appreciated. So usually we talk about, we invoke the partial transpose, whereas for physicists it is important to know that it is partial time reversal. And another famous move in quantum information was the discovery of enhanced quantum algorithms. The discovery that quantum computers, quantum algorithms might overcome classical algorithms. Now, the thing had started from Feynman, who in 1982 explained that there must be an exponential slowdown if you want to simulate a quantum process on a classical computer. Now, look, if there is a slowdown on the classical part, we can think of a speed up on the quantum part. So, indirectly, Feynman's claim would mean that classical algorithms may show a speed up, an exponential speed up, compared to classical algorithm targeting the same issue. Now, we had to wait some time until Shaw discovered his quantum algorithm. It was the first discovery of the exponential speed up. Moreover, it was, the speed up was pointed out, was discovered for a very, very important task, which was number factorization. That large numbers cannot be factorized for practical reasons using the fastest classical computers because factorization needs an exponential increase of resources. Therefore, the fact that you cannot factorize a sufficiently large integer using any advanced computers on Earth, this fact became the basis of the RSA cryptography protocol invented a long time ago. And if, according to Shaw, if we had a quantum computer and if we implemented his algorithm, then we would be able to break this very, very popular and widely used cryptographic code. Now, therefore, the Shaw discovery had an incredible impact on quantum information science and quantum, and also it got an incredible impact on financing these investigations. Now, the theoretical physicist's insight may be different we think that nature may not be so much interested in factorizing large numbers. It may be, but we are not sure, not yet sure. So we ask, what has been speeded up exponentially? Is that factorization or something else behind it? Now, it is obvious, and it has been obvious for everybody, that it was the period finding that was the heart of the Shor algorithm. He reduced the factorization issue to the issue of period finding, plus a few boring, at least for me, algebraic steps. Now, it is the period finding algorithm which could be accelerated exponentially if it is done on a quantum computer. So the Shor algorithm for a theoretical physicist may or should state this. It is about the exponential speed of period finding. Again, it has some consequences for a theoretical physicist, different from the consequences appreciated by cryptography experts or military experts. And this is the following. The exponential speed of period finding, nothing else than exponential speed of pattern recognition. And I'm sure that I questioned a few seconds ago, I questioned whether nature is interested in number factoring. But I'm sure that nature is interested and practicing and performing pattern recognition. And this may open a perspective toward the understanding the animal or human intellect, because I'm convinced that nature is doing pattern recognition in everywhere, not only in biology, but pattern recognition may be an essential part of how animal or human intellect works. And another experience, little and very personal. It's about the quantum circuit language, also very, very popular in quantum information context. Now, again, let's go back by decades before. On the very last page of von Neumann's book, you find the description of his detector. It is now called the von Neumann detector. The issue is that issue discussed by von Neumann is the following. We have a system, a quantum system, whose wave function is psi of x. X may be the coordinate of the system. And now we are interested, we want to measure x, the coordinate of the system. Now, von Neumann says that let's apply a detector. The detector is another system. It is prepared in a state where the wave function of this other system is phi of y. Y is the coordinate of the other system, and at the same time, y is the position of the pointer of this other system. We expect of this position to measure the coordinate x of the system of interest. Now, we prepare the pointer in a state around the origin. So we prepare the wave function of the detector in a state pegged around y equals 0. And now we couple the system and the detector using an interaction Hamiltonian, which is written here according to von Neumann. And if after the coupling, the initial composite state of the system and the detector, they were independent, so their initial composite wave function was just the product of the two wave functions. Now after the coupling, you get the new wave function, and look, the peak of the detector's wave function has shifted from 0 to x. So the pointer of the detector points to the coordinate that we wanted to measure. Now, after 70 years, von Neumann detector can be taught in a simple way. Young people who became interested in quantum information, quantum computation, are very familiar with the quantum circuit toolkit to represent simple qubit processes. Now, the von Neumann detector looks like this in current textbooks. You have the upper line for the system state and the lower line for the detector state. And this is just the gate called control NOT. And this will shift the initial 0 value of the detector into the value of the coordinate of our system of interest. So this is how things have become simpler and more transparent thanks to quantum information investigations. Now, let's. I don't need to tell you that this quantum circuit toolkit is very useful in many other conventional contexts of quantum theory. So I really think that in future textbooks we may exploit this quantum circuit toolbox to teach many conventional quantum knowledge, even for beginners in quantum mechanics. Now, let me show you this summary of the first and dominating part of my talk. Quantum information has changed and reformed our understanding of quantum mechanics. It sharpened and deepened our insight into the foundations. However, I gave very occasional and unfairly personal examples. The fruitful and fertilizing impact of quantum information on physics, on learning and teaching, let me emphasize, of quantum mechanics, will surely continue in the coming years. And keep your eyes open, young people and seniors. In qubit, there can be more physics than information. And I propose to move to the rest of my talk. Otherwise, I would have questions or remarks, but let's push them to the end. Something which is about my investigation, my personal, my current investigations, even unpublished results. In only three slides. The mechanical Schrödinger cat. Imagine a massive object, maybe a nano particle, but much heavier than Zeilinger's buckyballs. Imagine a small grain, small solid ball. Now, mechanical Schrödinger cat means that in principle you would prepare the ball in the superposition of two separate positions. Now, we think that such Schrödinger cats are apparently missing from nature, so we don't see them. Now, what we see is that even the massive objects are well localized. They may have some quantum spread illustrated here to some extent, but they never form such a Schrödinger cat. Now, who eliminates the Schrödinger cat? We got a proposal a long time ago that a hypothetic gravity-related decoherence or collapse mechanism may eliminate the Schrödinger cat and may guarantee that massive objects are always well localized, having only a very, very tiny quantum dispersion of the center of mass. Now, the strength of this proposed mechanism heavily depends on the mass resolution of the object. If we may consider the mass as flat, even, all over the bulk of this tiny object, then the collapse would take hours. The scale is set by the Newton constant, and mass is a mass density. Now, if the mass is like in case of common condensed matter, there are nuclei inside, so it's grainy, then our theory predicts much shorter time scale for the elimination of the Schrödinger cat, milliseconds. Now, we have somehow tested the behavior of mechanical Schrödinger cats, whether they are still there. And these topics, I use this slide to offer at least an up-to-date lecture for the interested, to say that it is quantum optomechanics, which is the basic experimental context where you can test the quantum mechanical behavior of tiny nano objects. And this field is much related to quantum information because in those experiments, single photons carrying 1 qubit are coupled to the phonons of those tiny mechanical objects. And it may happen that some good quantum communication technology can emerge out of this setup. A good quantum repeater, maybe. Okay, this is just of the most promising experiments to see if there are some limited Schrödinger-Cat behavior spread for mechanical or for the position, center of mass position of tiny mechanical objects, or there is no such remarkable quantum mechanical spread for them. And now this is a slide from a recent, for the most recent talk that I delivered some weeks before. And this is the summary of the DP model, how Schrödinger cats might be eliminated by the gravity-related collapse mechanism. And the crucial thing is that look at this elementary, look at this elementary thing here. Imagine you have this is fully classical for secondary school students. It's conceivable already. Look at a homogeneous ball of the mass density rho, make a hole through it, place a test object inside it, and measure it will perform a harmonic oscillation up and down, and calculate the frequency. The frequency is this: Newton constant, square root of the Newton constant times the density. Now, there are two characteristic values of the frequency. This 1 hour for if the density is the common water density, and it is 1 millisecond if is the nuclear density. Now, it turns out that in the DP model, the grainy common condensed matter Schrödinger cat would be eliminated at a rate of milliseconds. If the ball is of even mass density, it only happens in non-relativistic context. It only happens for superfluid helium. Then the rate of the collapse is the longer one. It is a result. This has nothing to do. I don't mean that the Schrödinger cat must have the nuclear density. If it is grainy, as it is indeed because of the nuclei, because the mass is being concentrated on the nuclei, then it comes out from the DP theory that the collapse rate is that high. The collapse rate for helium is that slow. Yes, this makes already an issue for the experimentalists. I show you what is beyond the DP theory, which is a proposal. The DP theory used to be characterized as a gravity-related collapse theory. It is hypothetical. In short, people used to say that gravity is the cause of the collapse. And this is not quite sure. The only role of gravity is that it parameterizes the collapse rate, and that's it. Now, I gave a twist to the concept. It is very, very radical twist, and I was not really sure that I was not going to fool myself or to lose part of my credit to propose that the gravitational field of a massive body is the consequence of the collapse. If there were no collapse at all, no collapses at all, there would be no gravitational field for a body. this is a very dangerous statement. But I decided not to. I decided that I might announce a new proposal. It says that the rate of creation of my gravitational field here depends on the rate of collapse. If the rate of collapse is lower, then the creation of, when I move, when I accelerate, when I am accelerating, then my own gravitational field is being delayed. By milliseconds. And the crazy consequence of this proposal would be, or the crazy consequence is that for a helium body, this delay would be much, much, much longer because the collapse rate, the dp collapse rate for helium is much, much lower. So thank you so much. Thank you for your patience. And